The first part is that I want to motivate the answer without derivation for the lowest order perturbation theory. But of course, that will not be sufficient for our purpose. Then I will back it up with a systematic derivation, okay, in a very standard way, so that later on, maybe in some of you, in your future research, you need to develop fourth order perturbation theory. At least you know what to do, okay? No guarantee that you can do it, but at least you know how to approach that problem, okay? So that is my plan. So let's start. Time-independent perturbation theory, all right? I'm motivated with what we want to get. In variational calculation, the theorem is restrictive. Okay, let me check. Okay, sorry, let me first check the departmental course page. Oh, okay, so how about this? Give me 3 minutes. I upload the notes. I thought I did that yesterday. Okay, so short break. Give me a minute. Okay, you can now find the perturbation 2 sets of notes up to here, up to now in the course page. Sorry about the confusion. I thought I did that. Okay. So this is the first page, okay, a new topic. Let me motivate it a bit. Remember, in the variational calculation, we are restricted by the theorem. It says, suit for the ground state energy. So we can comfortably apply that only to guess the ground state energy. But what if we want to know the second excited state or the 100th excited state? Can we do something about it? Okay, so that is a good question, and that motivated perturbation theory. So let me explain what perturbation theory would like to do. First of all, in perturbation theory, we must have a labeling problem, okay? A problem that is close to your actual problem that you know how to solve exactly. Okay, that is the first thing. For example, infinite well. We know how to solve this. By that I mean, we know all the allowed energy that I use a subscript 0 here means this is the 0th order problem, meaning the exactly solvable problem. And I know every one of them and the quantum number, okay? So these are all the energies, these are all the energy eigenfunctions. We have to have a problem that we know how to solve. That will define something called the H0 part of the problem. Then we use this to solve some harder problem. For example, how about this problem? We don't know how to solve, but we want to know all the eigenstate or eigenvalues, meaning all the allowed energies and all the wave functions go with these allowed energies. We are not restricting ourselves only to ask about ground state. Okay? And how about this one? We like this problem a lot, right? I use this as an example, easy to see. Okay? And now we want to ask the following. How about the seventh energy of this problem? I call it E7. But we realize that this problem is not too far away from this known problem. So we want to do something like the seventh energy of this problem may be close to the seventh energy of the known problem that we know, right? 49 times this thing, all right? Okay? But there must be some correction due to the difference between this problem and that problem. Okay? So we want to look for these corrections due to the change in the u of x, flat versus V-shaped, well, inverted V-shape, okay? Similarly, we also want to ask, what is the seventh wave function, energy eigenfunction? What is it? Well, we can't solve it exactly. Nobody knows how to do it. But then we want to do something like this. It should be rather close to the known one for the solvable problem. Okay, I mean this with 7 here. But that should not be equal to that because they are different problems. We hope to look for the corrections due to the changes between this problem and the known problem. Okay, so is the goal clear? Okay. 得唔得？行不行 ？Okay. Now, just to remind you, we are asking questions beyond the ground state. Okay, so we are trying to do something not only for the ground state, but beyond it. Okay, so we are more ambitious here. But that comes with a price. We have to pay a price. The price is that we ought to know how to do a part of the problem, the part that is exactly solvable. Okay, so we have to identify a part that we know how to solve. Otherwise, we don't have anything to start doing the perturbation problem. Okay, so more ambitious on one hand, but we ought to be more well prepared on the other hand. Fair enough, right? That's life. Okay, you want to get more, you have to be prepared better. So in order to start a perturbation scheme, a perturbation calculation, we ought to be able to identify from the problem what is H0, what is H prime. Sound trivial, right? But this is really step number 1. If you don't even know what is the solvable part, and then you can't know what is the perturbation term. All right? This H prime will be called the perturbation term. So let's practice. Mathematically, we have an H that we don't know how to solve, but we want to do perturbation. Then we need to inspect the H so that a big part of the problem called H0 is a solvable problem. Okay? So I called it, it is a nearby problem that can be solved exactly. All right. So in our mind, this H0 may be 90% of H already. The rest, the part that makes the problem insolvable, is only a small part of the whole problem. Okay, so that is the idea. So with this, we can write our bad problem as the part that we know how to solve plus the extra term. And this term defines what is the perturbation term. Okay. Example. If this is the actual problem and this is your H0, you know how to solve this. The definition of H prime is H minus H0, right? From here, you know how to define H prime, right? Put it to the other side, okay? So now, realizing that H prime for the problem is, now pay attention, 0 out here because it's infinite minus infinity, okay? So it is nothing outside the well, and this linear line inside the well, and that is your perturbation term. Okay, is that clear? Okay. Now I throw at you a different choice. Right? Now, what if my H0 is a flat bottom well up here? You know what I'm saying? First choice, I can make it to be here, flat here. I can make also do it like this, okay? So the actual one will be here, okay? So in that case, your H prime will have the same form, but the number will be different. The bottom will start from here, go down negative. Do you see? Okay, so do you understand what I'm saying? Hey, are you around? Okay. So the point I want to make is that there is no universal choice. Okay? Given a problem, the first thing is to exercise what you know. Identify H0, and then you can write down H prime. All right? So this is the problem that we have been doing, okay? So now, only after that, you look for H0, you know all the answers. These are taken as known, okay? Then you want to solve this problem, you want to ask about E13. Then I can say, perhaps it is E13 zeroth order plus some correction. The correction must be due to H prime. Okay, this is what we want to do. So in a very pictorial way, our goal is to do something like this. We have a part of the problem that we know how to solve. So I draw out all the energies, they are known. We have a problem that we don't know how to solve. Nonetheless, we know that the allowed energies are there for us to solve. They exist, that is to say, but we don't know the value. So I plot these crosses here. Okay, they are not known. We want to take this answer in a systematic way, hopefully, to get closer and closer to this unknown value by taking into account of this H prime in an order by order way. First order, maybe I take this value to some value here that is not bad, but not so good. Then I may need to do second order in H prime to get closer to the actual value, okay? So this is the first order, second order perturbation theory. That is what it means, okay? So this is our goal, doing this to take the value from the known problem to the unknown problem. Similarly for the wave function. Therefore, to do any perturbation theory, you ought to know something, some background, especially those problems that are solvable. If you look back in your first course, last term or the year before with me, actually you don't have that many solvable problems. 1, 2, 3 dimension infinite wells, 1, 2, 3 dimensional harmonic oscillators, something called the rotor, a rod rotating, okay? I know Professor Liu did that. And then spherical symmetrical potential, you know that's YLM theta phi stuff, hydrogen atom. That's basically all the exactly solvable problems that you have, okay? Plus a bit smaller problem called the spin one, the 2 by 2 matrix, you can usually solve it exactly because the matrix is small, okay? If you don't know this, you have no way to start a perturbation theory because you don't have an H0 part of the problem, okay? Then you better review these solvable problems. Otherwise, you get nowhere. Okay, then we get at the first result. First order correction in the energy, okay? So this will be the first result you encounter. The way I want to do it is hand-waving argument. That is to say, don't derive it, okay? So what is the problem? Already discussed. I have an unknown, well, known problem, but don't know how to solve, H, in which there is a big part solvable, H0. I know this, I don't know that. And I know that this change must be due to H prime, the perturbation term, okay? So let's see what's known, what is unknown. We know the eigenvalue and eigenfunctions for H0. After we identify H0, we know what is the perturbation term, okay? Now, let's look at what we are asking. We want to know the first correction term due to H prime. By that one order, I mean first means first order, okay? Let's see what do we have. Let's say we are focusing on the nth eigenvalue, En, all right? En is an energy. What do we know? We know the 0th order wave function phi n0. That is the known part, okay? For example, the 7th state of the infinite well, of course, you know, is sine 7 pi x over a, okay? Something like that. We know that. And then we know you are given the problem to solve. Okay, that is to say the Hamiltonian is known. How could you form an energy out of these things? Okay, you know the unperturbed state, you know the H, which carries automatically one H prime. You have a state, you have a Hamiltonian. We want an energy. That's the question. Okay? the answer that I will try is, what else can it be? Energy expectation value. Okay, so that is my claim of the reason. What else can it be? A state, a Hamiltonian. So let us try to see what it is. So I will try to calculate an energy out with my limited resources. I only know two things. The problem you give me, and then I identify the exactly solvable one. There is a wave function for the state that you're asking, the nth one. So look at this expression. The state on the left-hand side is unrelated to h prime, so-called zeroth order in h prime. The state on the right-hand side is zeroth order in h prime. It has to do with h0. And h is h0 plus h prime. So there is one h prime automatically appeared. So you will pick up a term that is first order in h prime automatically. Okay, so do you see my argument? I'm guessing at the answer. Okay. Now, for those who like mathematics more than physical argument, hold on. The next part of the notes will give you the mathematical derivation. Okay. Now, that is a good question, Huang Hao. Okay. So Howard. Okay. For that, I would suggest let's hold on to the next part, in which I will give you a mathematical derivation. All right? Get it? Okay. But nonetheless, this is a very natural way to do, right? So let's carry on and look at the answer. So I'm claiming that first order energy can be obtained by doing this expectation value. Zeroth order unchanged wave function with h prime in between. H has a part of h0 and h prime. The first term, h0 phi n0, is exactly the eigenvalue problem of the known solvable problem that will give me the zeroth order energy times the eigenstate itself. So I have an integral like that. My exactly solvable problem, we know all the eigenstate, therefore we can normalize it before starting the calculation. It is normalized, so this is 1. So the 1 here, I don't need to write it out. The more interesting term is the second term. Here explicitly, I have zeroth order state, first order 1 factor h prime. So I copy it through. Now, at least, I didn't lie to you. We did get something of the form we want. We want the nth eigenvalue. As said, it should be the nth eigenvalue of the known problem plus some corrections. At this point, we have found the first correction term. There may be other term, second order in h prime, third order in h prime, and so on. Okay? But at least that is exactly the form we motivated the problem, the technique at the beginning. We want to look for corrections due to h prime. And h prime is indeed here, okay? So this will be the first order perturbation result for the energy. The form is expectation value of the 0th order wave function with respect to the perturbation term. Okay, meaning 0th order state, the exact eigenstate, same on both sides, in between the perturbation term. Okay, so this is an expectation value for H prime, right? By definition. Okay, so finally we get our first perturbation result. If you like this kind of notation, it is the first order term in energy. Okay, so in words, I think it's useful to it can be expressed. You can express the answer in words. So I write it out for you. It is the expectation value of the perturbation H prime with respect to the 0th order state, the unperturbed state. Okay, this thing together obviously is first order in H prime. Okay, so simple result, but I would say it's a very powerful result as well. It is one of the most important results in quantum mechanics. Rather simple, okay? A lot of, again, in understanding atom spin orbit interaction, for example, and then in molecules, okay, you can get a sense by applying this simple formula. Pretty nice to know, right? For those who like mathematics, to see it how it goes through like that will come later. Okay, here I just wave my hand. What else can it be? Let's apply it. This is our old friend, our problem. We don't know how to do this. We know how to do this. Thereby, this is our perturbation term in the cartoon way. But now we have to get our hands dirty. We need to do calculations. Therefore, we need to write down an expression. Linear, 0 at x, right? V at x equals a. What else can it be? This is the thing. Okay, get me? 0 outside, we don't need to care about integration outside. Okay, let's apply the formula. Very humble. We only want to see the ground state of this problem. What is the energy? Okay, what is the estimate of the energy? So from our formula, we know it is the ground state energy plus a correction term due to H prime, first order. So the ground state of the solvable infinite well is square root 2 over a sine function. Get me? But you have two of them, left and right. So the square root becomes 2 over a, multiplied together. You have a sine in here, the same form over on the right-hand side. In between, you have this perturbation. Plug it in, okay? So do you see that the second term, I'm applying our result. Okay? Now, the rest is just integration, nothing to do with physics, okay? So do that, it's something like that. Okay, Google it, someone will tell you the answer, all right? So at the end, try it, okay? You must try it, okay? I'm not kidding. So at the end, you see a lot of cancellations, okay? And then at the end, it is V over 2. Okay? So that is to say, for this order, the energy is what we get for the ground state energy of the flat bottom well, shift it up by V over 2. Well, I think that is what you guess, right? If you are in an interview, someone asks you, hey, give me a guess, ground state energy of this, okay? The roughest thing that comes to your mind is, okay, 0 here, V here, maybe on average is V over 2. So that is actually a series solution from first order perturbation theory, okay? Now, of course, we are not satisfied with this. Later on, when you learn how to do second order, you can have another term here that will decorate this result to be closer to the actual eigenvalue. Now it is an interesting exercise, not to do ground state only, but to do any state. It's easy to see that you will pick up this correction term just with an n inside instead of 1 here, okay? You do it again and again, you will find that it's again V over 2. So for first order perturbation only, this problem will shift all the eigenvalues of the solvable problem up by V over 2. It's just approximation. Nonetheless, you see the difference between today and last week. Last week, if I ask you, hey, tell me something about this problem, you say, I don't know, sorry. I don't know anything. But today, at least you can tell me something using perturbation to first order. You can tell me every state is shifted up by an amount. That is quite different. So I did the easy one. You can try the other ones, okay? So how about this? It will be interesting to first give yourself a guess. You guess what it is, and then you do the first order calculation and see, all right? Try it. It will be fun. And how about something like that? Okay, a rounded bottom. You can put a sine wave there. Okay, again, give it a guess and do the perturbation theory. You will have 3 sine functions come together. That is doable. Okay. On another hand, we know this harmonic oscillator problem, the exact solutions. So it will form, again, the X0 for many interesting problems. For example, a quartic term. We mentioned this problem in the variational calculation, but how about this? Not only asking for ground state, higher state, tell me something. At least now in one line, you can tell people that the energy is shifted by that to first order. That's pretty nice, okay? But of course, I also like to warn you, don't be carried away. First of all, at this point, make sure that you understand all the symbols. Unavoidable in perturbation theory because we have a solvable problem full of symbols, the exact eigenvalues, the exact eigenstate, and then the not solvable problem, the corresponding eigenvalue, eigenstate. So you ought to understand what the symbols are, okay? You don't need to derive the result again and again. You applied it, but applying it, you need to realize, I plug this thing into here, I plug that thing into there, right? Derivation will come next. Of course, we will not be satisfied with that. How about the next term, the term that follows here, the second order term? We will do it later, but we cannot guess at the result. We have to derive it, okay? We run out of insight. How about the first order correction to the state? we can only guess at a reasonable form for the energy correction to first order. How about the state? Okay. Again, we run out of insight. We need to derive it. Then, an important question is there any limitation? Will this formula run into trouble? Okay. Again, we have to go through the derivation and see at which point this result will be dangerous to apply, okay? And then when you encounter such situation, be careful, all right? So there are still work to do. That's what I want to say, okay? Don't be too happy, but you should be happy because now you have another tool in your box. Pretty good, okay? Next, take a pause. Let's make connection. In the first thing, last week, we wrote the time-independent Schrödinger equation into a big matrix problem, in which the matrix element is of this form, okay? Now, in perturbation theory, we have an H0 problem in which we know how to solve exactly for all eigenvalues and all eigenstates. So it becomes very natural to think about that. Since we have this set known, a natural choice will be, what if we use this complete set of H0 solutions to write this unknown problem into a big matrix? We can do it, right? We don't need to derive it again. The matrix element is this. And since these are eigenstates for H0 that are known, we can normalize it and make them orthogonal. Because H0 is Hermitian, we have the right to do that. Okay? So that will make Sji delta Ji. Nice. Okay? So now we can think about this suddenly not doing perturbation. Do it exactly. Okay? So if you do that exactly, I'm copying a result from last week, we will have a matrix like that. After you make this Sij equal delta Ij. This is exact, no approximation. Okay? Now, we just guess at the first order correction. Can we see what we have done within this context of writing it in a big matrix? Okay? So, do you understand my question at this point? Because the answer is very simple. My question is, I can take the exact solvable solutions to write the unknown problem into a big matrix, which is exact. On the other hand, we have the first order correction in energy, the formula. Question is, how can I connect that exact huge matrix problem to my approximated expression? Is the question clear? Okay. Hello, hello. Okay, now, on one hand, I have H0. Therefore, I have a complete set. Therefore, I can take that complete set and write the problem, the unknown problem, into a big matrix as what I highlight here. Okay, is that okay? That is one side of the problem. The second side of the problem is that we know one formula for perturbation, first order correction in energy. I have that. Okay. My question is there a way that I can connect this exact huge matrix to my first order perturbation theory. Okay? Then let's go back to our discussion on the huge matrix. If it stayed infinite by infinite, it is exact. If I do truncation, make it smaller, that will be approximation. Therefore, I must make some truncation so as to go with the approximation. Okay, so do you understand what I'm saying? Okay, so what is the truncation of this exact matrix for first order energy correction? Okay, now follow me. In principle, it is a very complicated thing. Now suddenly, okay, do something to your eyes and said, I can only see the diagonal elements and nothing else. Meaning, neglect all the off-diagonal elements. Okay? What does it mean? You are truncating this exact huge matrix into many one-by-one matrices. You only see the diagonal one, okay? And then the determinant will be diagonal multiplied, diagonal multiplied, diagonal, and then equals 0, right? So one term equals 0 will be the solution. Okay? So suddenly you ignore everything and only focus on the diagonal terms one by one. For example, HNN equals EN. And y. Okay? Now write it out. This is your approximated eigenvalue. Only look at the diagonal, it will become HNN. Therefore, this is our guess exactly. My hand-waving argument, same thing. And it will give us the first order perturbation result. Okay, so let me summarize. I guess at a first order correction in energy by saying that I have H, I have the 0th order state, I want a first order energy, what else can it be? Expectation value. We see some examples. Tilted well, I encourage you to do this V-shaped thing, circular thing, etc. And then I want to make connection with the exact infinite by infinite matrix. What is this first order amount to doing approximation to this big matrix? It turns out the approximation to this big matrix is ignore everything that is off diagonal, focusing only on the diagonal elements. The diagonal elements means one by one matrices, many of them. Okay, you pick any one equals 0, that is our first order energy perturbation. Okay, and I think that also answered earlier Howard's question. Okay, meaning if you want to take into something that is first order in the wave function, but keeping 0th order in the Hamiltonian and the other side, you have other terms that you need to worry about because that amounts to an off-diagonal term. Okay? You have off-diagonal term, then you can't take one off-diagonal term, for example, H35, and not taking H53 in. Therefore, that ought to be something higher order. Okay? But I know that answer is abstract, but if you hold on to the next part on Thursday, we will do the derivation step by step. Howard, happy? Okay, so I will stop here. today, basically that is all the main content, okay? The last page is just the pictorial way of what we have done, all right? So we have achieved something today. Variational calculation, linear combination of bases is a matrix problem, smaller. We have developed first order correction in energy perturbation theory, and then back it up as a way of the roughest truncation of the exact huge matrix, keeping only the diagonal term. That also tells us what to go forward. Second order perturbation means take into account something of the off diagonal terms. Okay? And that is exactly what we need to do for the second order perturbation theory. Okay? So see you on Thursday. One announcement, please. Exercise classes start today. If you have registered into one section, please go. The TA will do some examples for you. Seeing how things worked out is very important in learning applied quantum mechanics. We are not playing with formulas. We are playing with some numbers. Okay, the TA will show you some precise hydrogen spectrum data, telling you that what we learned up to this point is only a good approximation of the actual data. Okay, so attend exercise class, start doing your problem set. I see you on Thursday. Bye-bye.